Ah, ah, okay. Good morning, everyone. This is computational microelectronics lecture number 8. So after long pause due to my business trip and other national holidays, and we are now coming back to the offline lecture. So today's lecture is the 8th lecture, and we'll talk about a little bit about neural network and its application. So today's topic is neural network, but since it is okay, sorry about that. So let me just do it once again. Okay, now let's come back. Once again, welcome to the lecture 8 of our computational microelectronics course. We had a long pause due to my business trip and national holidays, and now we are coming back to the lecture room once again, and this is the 8th lecture. So up to lecture 7, so we have spent our time to learn about a little bit more about equilibrium properties of a MOS system. So maybe you have done your calculation of inversion charge density for this MOS structure. So for that purpose, we have studied Newton-Raphson method. So now you can calculate the solution of nonlinear equations. For why, we will just move to a little bit different topics on neural network. So today's lecture is just a brief introduction of application of neural network techniques to semiconductor device research. So today's lecture expected to be quite short. Okay, so in this course, computational microelectronics, actually our way of thinking is shown in below in this way. Basically, this course is for the ticket developers. So by attending this course or enrolling this course, you will learn how to program your own ticket programs. So numerical analysis of a set of governing equation means that set of governing equation in this case, for example, Poisson equation for electric field calculation. You have already done it for your one-dimensional MOS system, and you did certain numerical calculation. So basic procedure is shown here. You just identify governing equations for your system. For example, if you wanted to just calculate inversion charge density for given structure, then you are allowed to just solve Poisson equation. However, if you have to consider transport properties of your device, then in addition to this Poisson equation to calculate electric field, you have to also consider transport equations such as continuity equation and related current density expressions. So if you are going even further, nowadays, for example, I'm now talking about Poisson equation and transport equation, and nowadays it is getting more and more important to consider summer effect inside your device, because our devices are getting smaller and smaller and getting also more powerful, so they can generate a lot of heat inside the structure. So it means that they are working, that generated heat is working as a heat source inside your device. So even inside our system, some part becomes very hot, although other part is remaining as relatively cold, so we have to consider this kind of effect. Also, if we go to any further things, for example, so what can be any further thing? So if you are talking about a new device, for example, using ferroelectricity inside your device, then you have to also include some equations for determining the polarization of your ferroelectric material. Also, for example, if you are considering other different physical mechanisms in it, then you have to also consider that kind of physical mechanism or equations for those mechanisms in your set of equations. So first you have to identify what is good enough or sufficient govern a set of governing equations. So that is the first step you have to do. Yes, but more or less this is not identified by yourself, but usually when you select a certain model or certain problem, then governing equations are known to you. Then next step is discretization. So although your ultimate goal is numerical analysis, just brute force implementation usually does not work any further, because many cases governing equations are highly nonlinear, so it is very difficult to have a stable solution. That's the reason why we have some specialized technique to implement this program into the code. So for example, very important example of this discretization is shown here, and you can see that, for example, your electron current density should be discretized in this way. If you follow other ways, then maybe you will have certain problems in having a stable solution. Once you have your proper discretization scheme, then next step would be just programming. Now you have your own code and type them. Of course, you can introduce many mistakes and bugs in your program. Yes, that is our usual life, and you can make a certain debug process. After that, you are satisfied with your code. So that is a typical way we do in this computational microelectronics course. However, today's lecture content, neural network, is a new topic introduced only from this semester, because nowadays I feel that there are more and more interest on this data-driven approach. So although we are just entering into this stage, but I guess that after a few years later, maybe understanding the neural network will be just mandatory knowledge for our study in TCAD development. So that's the reason why, although I don't think that actually the application of neural networks to the real semiconductor problem is not matured. So we are still in its infant stage, but anyhow we have to prepare for future of TCAD researches. So I just prepared 3 different application areas in today's lecture, although I prepared initially 4, and the first one was for process simulation. So however, I now think that I'm not that much an expert on that process simulation, so I intentionally skipped that part. So we will just talk about device simulation related job. So the generation of semiconductor device structures, that is one of the most important application area of this neural network approach. However, that becomes too complicated, so please understand our discussion today is quite much limited to the device simulation only. The simplest model we can think about this neural network approach is so-called surrogate models. So surrogate means that instead of considering the full details of the original system, we wanted to make a much simplified work. Just inside it, it doesn't have any kind of a physical explanation, and just to generate the final result we wanted to know. For example, let's think about this one. Here we have an example of a surrogate model, and here we have a certain input files. We have no idea about what those numbers are exactly. It really depends on the situation, but point is this surrogate model made of a neural network, in this case a fully connected neural network, but that doesn't matter. How can we implement this one inside? But point is, yes and yes, we can calculate the breakdown voltage of our device and specific on resistance. This is on resistance. If you are interested with the simulation of a power device, you will find that actually these two parameters are the most important figure of merit. So by using these two numbers, you wanted to maximize the breakdown voltage of your device and try to reduce the on resistance of your device. So for your interest, I will explain a little bit more. Breakdown voltage means that when you just turn up your transistor and you wanted to apply very high drain voltage, but still wanted to have almost zero drain current. That is the situation. However, if you have a certain physical implementation of your semiconductor device, then eventually when you apply too high drain voltage, then there will be unwanted current conduction. So this condition, ID is very small, cannot be satisfied any further. That is called as a breakdown, and the onset of that breakdown phenomena is the voltage where the breakdown phenomena occurs is called as a breakdown voltage. So if you have a high breakdown voltage, then this is regarded as a good device, and if you have a relatively low breakdown voltage, then that is considered as a poor device when you apply it to the power device application. And on contrast to this breakdown voltage, which is related with its off-state current, on current is related with its on condition. So when it is turned on, when gate voltage is high enough, then actually the resistance obtained from this device operation should be minimized. If that is minimized, then it means that the switch itself does not consume much power. However, if we have a very high on resistance, then switch itself consumes a lot of voltage, so that will give us a certain overhead in the switch performance. So we wanted to minimize also this on resistance. Of course, they have the relation of a trade-off. If you try to make it high, so if you wanted to have a high breakdown voltage, the way is quite easy. If you introduce very long reason with relatively low conductivity, then you can easily increase this breakdown voltage. However, that directly affects that increase of your own resistance. So since they are in the trade-off relation, so you have to find out the optimal point for your own purpose. So now you understand, in the case of our power device application, the calculation of breakdown voltage and own resistance, that is quite important. But point is, how can you obtain best optimal device design? So we must change certain parameters, certain device parameters, and measure or calculate this final quantity. If it is not that much satisfying, then we have to repeatedly change these parameters, and we must do this tedious step again and again and again. So that will take forever. So the point is, if we can generate a surrogate model for a certain power device technology, then once that is established, then without concerning the performance of our TCAD simulation, by using this simplified model, we can always try to find the best model we can have. Point is, the build up or building this surrogate model itself takes a certain time. Once we can make it good enough surrogate model, then everything will be quite happy. But in order to generate this one, then we have to prepare a lot of TCAD data set obtained for this device template. Yes, for example, if you have a 500 TCAD simulation result or 1000 TCAD simulation result, then you will have a vector of your input parameters and out vector of your breakdown voltage and known resistance, and your certain neural network can learn this model quite efficiently. But please, this learning itself doesn't take much time, but preparing 500 or 1000 TCAD simulation data, that takes quite a long time. So if your template is very precious, and if it is the final version of your technology development, then it's okay, because once you build this surrogate model, then you can reuse this model again and again. Then that will give you tremendous advantages of conventional TCAD simulation. But point is, if you are in the stage of just modifying many things during your technology development, and unfortunately, actually development itself is always changing something for better performance. For example, this is your template. Oh, but I don't want to have the field plate any further. I want to kick out this field plate. Then what will happen? If your surrogate model just considers the structure with the field plate, and when you kick out this field plate feature, then it cannot be used any further. So strictly, this surrogate model is binded to the template you are considering. So that is one thing. So yes, so of course, in real situation, in your industry experience, then maybe you have two important device templates for your own task. So in that case, you can use this kind of a surrogate model approach. Once you successfully generate this surrogate model, then just applying surrogate model doesn't take time. So it can be just performed within microsecond or millisecond using our conventional PC. However, TCAD how long does it take? It will take several minutes or hours or days. So the huge improvement of simulation time can be expected. And if it is well done, then you know that this is actual value and predicted value means that this empty triangle, blue triangle, is just predicted by a surrogate model. So it doesn't take time. And these red dots are obtained from ticket simulation. So each dot, red dot, requires several minutes or hours to be obtained. So you can expect a lot of performance gain. Okay. So this is in my opinion, the simplest approach we can use, the neural network approach. Simply speaking, it is just to use the descriptor for our output variable, output parameter in terms of our input parameter. We don't have to think about how can we express input and output parameters. For example, in the case of our compact model, we have to find out certain thing, QE versus gate voltage. In order to get this information, what you did was starting from the well-established Poisson equation and rigorously integrated in your paper or in your notebook. After that, you get certain well-established complicated expression and numerically solve that equation. So finding the relation between this QE and VG, that was the exact relation. However, that cost a lot of human effort. However, if you just have this kind of neural network and just collect the simulation data and dump it to your neural network, then neural network can do anything for you blindly. So it sounds quite attractive, but point is, if you apply your parameters beyond the training range, for example, you have tested your oxide thickness starting from 1 nanometer and 10 nanometer, and you have a perfect match for all kinds of your calculation. But for certain reason, instead of this 10 nanometer, let's assume that you have introduced now 200 nanometer thick oxide thickness in your technology. Then what will happen? Well, this relation neural network to describe this given range, maybe it can work, maybe not. So there is no guarantee for us to have reasonable description about this problem. Okay. And another one is more related to our own research work. Okay, so surrogate model doesn't consider the internal physics, and therefore, although it says that VV will be that value and on current on resistance will be that value, but we have no trust on the generated result. We just have to believe that those results are correct enough. So instead of that, if we are working with ticket simulation, then actually we can use this neural network to accelerate the ticket simulation. Finally, we still get the converged ticket simulation result. So accuracy is guaranteed. However, the time required to get the converged solution can be reduced. For example, in my opinion, actually the best institute or research group working on this field is Samsung. So they have nowadays publishing tons of papers about how can we use the neural network like approaches to accelerated TCAD simulation. They have dedicated team or dedicated research group, although not that large, but they are devoted to developing this kind of approach. For example, you are now looking at so-called neural drift diffusion model uh, presented in this year's CSPAD just a few weeks ago, and now you can see this one. For example, this is a conventional TCAD simulation, and this is a doping profile of your device. So what does it mean? So this is corresponding to your substrate, and here and there you have a source and drain contact. And what is this? This is just covered by metal and metal, so not included in the simulation domain. So in this case, if we have a certain neural drift diffusion model, then from this doping profile it can generate, for example, electrostatic potential, usually written in our lecture material 5, and electron density written in N, hole density written in P. So for that purpose, of course, they have to train their something. We have a little idea about what is exactly inside it, but once we have a doping profile of our device, then it can predict, oh, under this condition with this doping profile, maybe electrostatic potential will look like this, and electron density, hole density. Of course, this law just shows TCAD simulation result, so this is deterministic and this is the ground truth. But point is, if we have a so-called neural drift diffusion model, then when an unseen doping profile is given, then it can at least try to generate so similar quantities like electrostatic potential and carrier densities. How do you feel about their resemblance? In my opinion, actually it looks quite excellent because NDD laws just same with the TCAD laws. So if we have this good enough internal quantities, then by using these internal quantities as initial guesses for your simulation, then you can get certain TCAD acceleration. So although, well, Samsung usually doesn't show those kind of acceleration results in their publication, but we can do similar thing by ourselves. So in our research group, we can also try similar things. Then you can see that compared with the conventional way of our TCAD simulation, so changing the bias condition continuously and slightly, so we can accelerate our TCAD simulation at a given bias condition about 10 times, and this 10 times or a few times is the thing we can expect from this kind of approach up to now. Not 100 times or 1,000 times faster, because this kind of calculation is eventually related with certain calculation, so we have to do. So compared with the previous one, wow, it is super fast. Once we make it, then actually it can generate a lot of data without spending seconds. However, internally it has no physical mechanisms, and if we ask, for example, what is the potential profile when we have the breakdown case, then this surrogate model cannot give us any information. It just estimate that for this device maybe the breakdown voltage would be about 250 volt. That is the thing we can have out of this surrogate model. And in the case of this TCAD acceleration part, then yes, 250. Then if we ask to our engineers or our colleagues to generate that internal profile, then they can provide us also solutions for those ones. So, well, I think that this is a more realistic and feasible way to do it, and we are actively working on that. Another very important application is compact model. Compact model is so maybe you are now already experiencing the compact model. What you have done up to lecture 7 is just the starting point of building a compact model. What you have done is you started from the Poisson equation. Do you remember? And you just integrate your Poisson equation by multiplying the electric field, and it was integrated over your simulation domain. And what was the result of this evaluation? Then you were able to get square of your, not inversion charge, but square of your total charge inside the semiconductor device, semiconductor substrate, and it was written as a function of a surface potential. That was you have done. Simply speaking, this is the very basic part of a compact model. Once you have this relation between inversion charge and surface potential, then along the channel direction, here we have source and drain, we can consider many different slabs. Of course, each of them is treated as an MOS structure, and by integrating this inversion charge with respect to or inversion charge along this channel direction, x direction, then you will get a certain quantity related with drain current. Once you have this drain current, then by adding further physical mechanisms like Schottner effect or velocity saturation, mobility degradation, all kinds of leakage current, blah blah blah, then you can get a relatively simple expression for your terminal currents. Means that you can generate a drain current model, source current model, even gate current model, and if you have a substrate, then you can also generate a model for substrate current. So it means that although it is much simpler than TCAD simulation, but it has its own logic. I mean that although it is simplified, but why that is expressed in this way, then we can trace back to the governing equation. For example, if you are asked why we have this kind of relation between square of semiconductor charge and surface potential, so although you cannot answer it quite rapidly, but if we trace back to this derivation procedure, then you will eventually find that the starting point was Poisson equation weighted with the electric field. So please don't be confused with the previous approaches, surrogate model and compact model. Compact model, although simplified, but it has its own physical reasoning. And in this case, once you get this compact model, then that can be used in our famous program called as SPICE. And this SPICE is the program used by our colleagues, device circuit designers, and they are designing the circuit with the SPICE program or even higher level tools. So therefore, compact model is the very basic starting point of designing the semiconductor chip. So it is extremely important, and there is a standard model example BSIM CMG. So BSIM is a family of compact models, and this B starts from Berkeley, UC Berkeley, and there is a group which is dedicated to the development of this model, and this is industry standard one. So so currently we have a well-established standard model called as BSIM CMG. So there are so many different BSIMs. For example, earlier one was called as BSIM 3, the version 3, BSIM 4, BSIM 5, blah blah blah. There are many of them, and after that they have named, for example, IMG or other ones. But nowadays, the most relevant one to us, living in the age of FinFET and gate-all-around transistor, is BSIM CMG. What is BSIM CMG? So CMG means that common gate. So gates of our transistors are all common. Why we have this kind of description? When the multi-gate MOSFET was first introduced, so it has such kind of structure. So this is a silicon, and it has top oxide, and it has bottom oxide, and here we have top gate metal, and here we have bottom gate metal, and there is no guarantee that this gate voltage applied to the top and gate voltage applied to bottom are the same. They were able to be modified or applied separately. For example, you apply very low voltage for your bottom gate and apply only high voltage to your top gate. That was possible. So that's the reason why we have independent gate. However, nowadays when you consider your FinFET or your gate-all-around transistor, do you expect several different gate voltages for your channel? So actually you don't. Actually you consider just one single gate metal covering all around your channel region. So nowadays CMG version is widely used and most relevant. Well, actually people are happy with BSIM CMD except for its slow calculation speed. Okay, so basically this kind of BSIM model, it is actually from our perspective, these models are extremely fast. However, the problem is we are not the user of BSIM CMG model. Actually, designers are using this BSIM CMG model, and they don't consider a single device. They are considering thousands of devices at the same time and learn quite a long time to get certain transient behavior of our circuit. So therefore, although each BSIM CMD model can be quite fast from our perspectives, however, reducing the simulation time or calculation time for each BSIM model is quite important. For example, if you can cut the simulation time factor of 2, so for example 50% less. simulation time, then what will happen? Your days or your week can be just a few days, or your months can be just 2 weeks. So it is huge improvement. So that's the reason why some people think that okay, BCMC is accurate, good, but that is slow. We wanted to make even faster. So that's the reason why sometimes people try to develop such kind of thing called neural network compact model. So also in this CISPAD, this year CISPAD, BSIM group themselves presented their own version, BSIM neural network. So it means that internally they introduce such a kind of neural network, and their input parameters are shown here. Gate voltage, drain voltage, they are just a basic one, and of course we can change length and width and oxide thickness of our MOSFETs. Then in traditional BSIM CMG model, then from these quantities, just they try to make certain calculations internally, although not as complicated as the TCAD simulation. But for example, from this one, they generate a COX quantity. Oh, this is the capacitance of our oxide layer. So if this is high, then we have higher ability to, superior ability to collect our electrons beneath of our oxide layer. So this kind of calculation is actually done inside the BSIM CMG model. However, in the case of a neural network model, they don't care. What does it mean? I don't know. Just input and outputs are provided, and this neural network try to study or mimic the behavior between input and output ones. Okay, so in many cases what we have to calculate is just a few. I mean that the one we have to calculate is drain current, source current, gate current, and if we have substrate and substrate current. And nowadays sometimes we don't have it. And also charges related with those 3 or 4 terminals. So there are not many output variables, and instead we have a long list of input parameters because they are all related with the layout. If the designer make a longer and wider device or shorter and narrower device, our BSIM model should support all kinds of layout variation. Also technology can change, so EOT can be increased or decreased, so our model should be able to describe all kinds of these variation in the input parameters. So anyway, they can do it, and after spending some effort, then they can fit the output characteristics amazingly. For example, here you can see red lines and blue dots. Blue dots are coming from the reference data, and here red lines are obtained from BSIM neural network model. The agreement looks amazing. It is because already this model has well trained to reproduce these blue dots. So yes, that is expected. So maybe we can use it for our own purpose, designing something. But point is it really faster than BSIM CMG? So internally we have complicated neural network. So the many of those ideas to introduce neural network was coined by the faster speed expected from this neural network. But actually many implementation could not accelerate the simulation because calculation of this complicated function sometimes takes a longer time than just highly optimized BCMG simulation. But the Berkeley group themselves says that okay, if we change the way of implementation a little bit, then we can get a few times faster simulation than BCMG. That was reported in this year CISPAD. Okay. Well, but this is a really serious thing, because our entire semiconductor industry is relying on this BCM model. Actually, nowadays BCM CMG model. So changing the BCM model is really difficult, and if that is 100% guaranteed that this model perfectly matched to the standard BCM CMG model, nobody will try to change from well-established model to this experimental model. And we have to show 100% compatibility and much faster execution time, or shorter execution time than BCM CMG. That is required. I'm not quite sure how the things will go in near future. And I wanted to mention that also there is a Korean startup company called as RSemi, and they are also developing similar models. Yes, so they are also publishing some their own approach to make neural compact model. Although I'm showing just BCM group and RSemi, but there are many other research groups who are trying to build this compact neural model. Yes, so because it sounds really attractive, because compact model is really a big deal. If you can make a certain change in the compact model, the impact will be really huge. But point is, well, do we have some chances? So I'm not quite sure. Okay, so up to now, I just introduce a few examples or a few application areas of neural network approaches, especially in the area of TCAD or device simulation and modeling. However, as I told you before, I intentionally excluded the discussion about the process-related one. But in my opinion, more important one is process-related one, because that can give us huge benefits when we really apply this kind of a neural network approaches. But unfortunately, much information is not disclosed to us, because this is too important sometimes to industry guys, so they don't disclose their precious experience to public. So I feel that I have not that much expertise to discuss or review all kinds of this research activities actually happening in the industry. But that this is really important, and that's the reason why today or in the next lecture we will build a neural network by ourselves without relying on any library. So nowadays we have many excellent libraries, so even young kids can generate this kind of a building a neural network and training something. But I don't think that the philosophy of our course, this computational microanalysis, is not relying on using the library. What we wanted to do is just to build or invent the wheel. So reinvent the wheel again and again, because after that you can invent any other things by yourself. So today's lecture will end with just the introduction of the very basic data set for our later use. So this is a MNIST data set of a handwritten digit, so we can download it. So please visit this address and try to download your own version. So I actually tried the original one. However, at least to me, I had no permit to download those original ones. So instead, I searched the web and found that in CSV file version it was available. I downloaded it to my local computer, so I expect that all of you can do it by yourself. Its size was about 100 megabytes, so it's not that big in nowadays, so you can do it. When you open the file in Excel, for example, this was loaded in Excel, but you can use many different programs to load this file, the CSV file. Then you can find many different rows. So this is 1, 2, 3, 4, and each row is assigned to handwritten image. So it means that this is 7, and this is the topmost pixel, and this another line is next pixel, and another one is next pixel. Here you have 28 numbers, and after 28 numbers are done, then your 29th number is now representing the image, pixel image at this point. So 2, 1, and now you have a next one, and here you have another 28. So eventually you will have 28 by 28, so you will have a square image created by these guys, Professor Van Luken's group, and you will have, if I remember correctly, the product between 28 and 28 will be 784. Together with this number 7, so you will have eventually 785 numbers in a row. So, and you have many means that about 10k or 60k. You have many different rows for handwritten data. So this is numbers. 0 means that just background, and 255, so this is the highest value you can expect as an integer number in this format, and that introduced the black ink. So for example, yes, this point is regarded as 255, and this point is regarded as just 0. So today's homework is quite simple. Instead of doing any kinds of numerical calculation, just download this MNIST data set and try to visualize it. So this is the image generated from this first line. So I just took this first line, and from this one I was able to draw this one. So in this case, this yellow one is corresponding to most closely 255, and this this part is corresponding to almost the number close to 0. So please try to build your own visualization about this data set. So what we will do in the next lecture will be just build a neural network. not train the neural network, but I will provide you the predefined neural network, and by just constructing or implementing that neural network, you will find that although we have no idea about how can this neural network can understand or recognize different digits, but you will find that anyway it works for your own handwriting. For example, if you say, if I write down this, what is it? So it is my 1. What is it? This is my number 2. And what is it? This is my number, oh sorry, this is my number 7 and this is my number 2. So we'll see that our predefined, pre-trained neural network can recognize our own hand drawing. So that will be the lecture contents of our next lecture. Well, I'm not quite sure whether we can build eventually the training system for our neural network. Maybe that will be too much for ourselves, building our own library for that one. So maybe we will stop there and coming back to our original ticket related job. But you know, the situations are always changing, and we should be open to new research trend. So that's the reason why, although that is quite primitive, we are now starting to the exposure or coverage of our neural network related stuff. Okay, so thank you for your attention. So although we have 10 minutes left, but I will directly wrap up today's lecture, and please submit your homework problem before our lecture start. Thank you for your attention.